Welcome. We're now going to turn our attention to model complexity, overfitting, and cross-validation. So our objectives are to see how we can create more complex decision boundaries from measured data, and then examine how these more complex models and their performance trade off in the presence of noise and errors and limited training data. That will lead us to the idea of cross-validation for measuring the performance of our classifiers. So let's revisit our classification problem and assume, again, for purposes of example, we're interested in classifying whether a face is happy or sad. We measure some features related to the mouth, and then we're somehow going to use these features, these measurements, to form a classifier. And our classifier will say that if the sign of the inner product of X transpose with some vector W is positive, we classify the face as happy. If the sign is negative, we classify it as sad. So our decision boundary is when the inner product between our feature vector X and W is equal to 0, because that defines where we transition from a positive sign to a negative sign. Suppose we construct the feature vector just by putting those two measurements into X. Then our boundary is going to be x1 w1 plus x2 w2 is equal to 0, which I can solve for x2 to write that as negative w1 divided by w2 times x1. Well, this is just the equation for a line whose slope is negative w1 divided by w2. So if I look at my x1, x2 space, my decision boundary is a line that goes through the origin. Now that could be problematic if our data is not well classified by a decision going through the origin. So we want to be able to generalize this to get some other types of boundaries. Let's suppose we add a constant to the feature vectors. So now we have our measurement x1, our measurement x2, and we'll add 1 here. Can solve for x2 again, as we did above, to write x2 is negative w1 over w2 x1 minus w3 over w2. So this is the equation for a line with a slope negative w1 over w2 and an intercept negative w3 divided by w2. So by adding this constant term, we've allowed our decision boundary to have an arbitrary intercept. And thus, with this feature vector, we have an arbitrary line as our decision boundary. So that might do a little bit better if our data is divided up as we had in this case. Well, suppose that we really want to have a nonlinear boundary. In other words, we want to have some curve which is not a line. It turns out that our strategy that we used a moment ago to get the non-zero y-intercept can be generalized to get more complicated boundaries. For example, let's suppose I throw in an x1 squared term into my feature vector. So I'm including the measurement x1, the measurement x2, the square of the measurement x1, and then the constant 1. If I look at my decision boundary where x transpose w is equal to 0, in this case I can solve for x2 and I end up with x2 being a quadratic function of x1, and thus I've managed to accomplish a parabolic boundary. And thus, I've managed to reach a parabolic boundary. And the exact shape of that boundary is going to depend on how I choose my w's. So in general, this suggests that we can get arbitrarily complex boundaries by augmenting different functions into the feature vector. So here I'm showing a case where we're including the product x1 times x2, x1 squared, x2 squared, x1 squared times x2, and so on. We can keep taking functions of our measured data values and create a feature vector which gets bigger and bigger. And by doing this, we can implement an arbitrary complex boundary. So if our data were distributed as shown here with the pluses and the minuses, we could implement this boundary that followed a very complicated shape. Now if you notice that this general feature vector also includes the simpler cases. If we were to set the w's associated with all these higher order terms that we added equal to 0, then I would get a linear boundary. So why not just use a very complex feature vector and allow that to automatically decide where our boundary is going to be? Well, this turns out to be too good to be true. And one of the things that you notice is as I increase the number of terms in this feature vector, the number of model parameters increases as well. Basically, the amount of training data and the quality of that training data places limits on how complex a boundary we can effectively use and still obtain good performance. In practice, almost all of our measured data is going to be contaminated by some level of noise and perhaps even some errors. Here I've shown some training data where I have this sad face that is apparently in the midst of some happy faces. I'm going to create a boundary that reaches out, circles around that sad face, and goes back so that I don't have any errors with my decision boundary. However, what if the reason this value shows up here is because there was some measurement error and this does not correspond to an actual measurement? Well, then you might say if I knew that was an error, I would choose a revised boundary given by the lighter pink color. In other words, I just choose the simpler straight line boundary and not worry about this term that has some error in it. Well, a second issue is that in practice we have a limited quantity of training data where we have features and known labels for that features. If I use a limited quantity of training data, I might end up trying to find a fairly complicated boundary that follows the trends I see in that training data. And what I've done in this boundary is I've tried to split the difference between the samples that I have in my training set. But if I were to accumulate more data, maybe the situation is actually like this. In other words, these artificial ripples that appear to be appropriate here really aren't, because if I had more data, I'd find out that the decision boundary was actually more similar to a straight line. So if we have a limited amount of training data, it can be difficult to determine where a very complex boundary should lie. Now, ultimately, when we choose a decision boundary, our goal should be that our classifier generalizes well to new data. We already know the answers for the training data, so to some extent, how well we perform in that training data only matters if that performance translates to new data. So these examples that we've looked at above are examples of overfitting, where we used a too complex of a model for the available training data. Now you can show that as we increase the model complexity, in other words, more terms in the feature vector, more parameters in W, then P, which we're calling the number of parameters in W, is going to increase, and the training error is always going to decrease. So a more complex model will always have a smaller training error, but it may not generalize well to new data, like these examples that we showed here. As a general rule, we want the number of parameters in our model to be significantly less than the number of our training samples, and that will help us avoid some of this overfitting. Cross-validation is an extremely useful tool for addressing these issues, and it allows us to measure how well the model generalizes beyond the training data. It's a very simple idea behind it, and what we do is we take a subset of our training data and we use that training data to learn the model. And we use the data that we didn't include in learning the model to evaluate the performance. So we hold some of the data out from the training process, and then that holdout data is used to evaluate the performance or to see how well the model generalizes. We can formalize these ideas in more detail by taking our available training data. We have features xi and labels associated with those features yi. We'll assume there's a total of n of those, and we take this set of training data and we're going to divide it up into capital M groups. We'll call each group S sub j, and there's M groups S sub j. So I'm assuming that the indices of the training data in group Sj are drawn from some set of integers Qj. So what we're going to do then is we'll start off, we'll learn a model W1 using the sets S2, S3 through Sm. So in this case, we're learning W1 by holding out S1 from the training process. So once we learn this model, we can compute the error that we would get, we'll call that E1, on the set of data in S1. And I'm going to normalize the classification error averaged over all the samples in the set S1 by the number of terms in the set S1, which I'm denoting as the cardinality here of Q1. We're just dividing by the number of terms, and we're summing the classification error over all of the samples in our held out set S1. Well, now we can use a different set of holdout data. Let's suppose we learn a model W2 by having holdout data S2. In other words, we train W2 using S1, S3, and then all the way up through SM. We can compute an error associated with the holdout set S2 from W2 in a similar manner that we did for W1. And we can continue this process over all the different permutations of possible holdout sets. And ultimately, we're going to be determining a model WM using SM as a holdout set. So we've trained our model using S1, S2 through SM-1, and we can compute an error on that holdout set from WM and the set SM. Once we've gone through that process, we can define the average cross-validation error, E, as simply the error across all of the M holdout sets divided by the number of sets. So in each case where we have a different holdout set, we're evaluating how well a model learned from part of the data predicts a different set of the data. And this is a surrogate for generalizing to data that we don't have. In other words, we're trying to predict how well is this classifier going to perform when we get new data that we haven't seen during training. Cross-validation is very useful then for comparing different models, especially models of different complexity. In general, you're going to prefer the model that has the smaller cross-validation score or the smaller error averaged over the holdout sets, because that model is doing a better job of generalizing to new data. And this allows us to manage or evaluate the trade-off that occurs with model complexity. And classically in statistics, this kind of trade-off is called a bias-variance trade-off. The notion of bias refers to the fact that our model may not be complex enough to capture the actual decision boundary. On the other hand, the notion of variance refers to the fact that there may be some variability or noise associated with the training data, and we may incur errors when we generalize if we try to fit the training data too closely. So we're trying to find a balance between the complexity of our model, in other words, that captures the actual trends in the data, against these sort of random errors that can occur when we overfit the data. In the preceding slides, we looked at applying cross-validation to the problem of classification. Well, if you're interested in building models for data, the same considerations apply. Cross-validation can be used to select a model of the appropriate complexity. As in the classification example we illustrated, we're going to define training data sets and holdout data sets, and then we're going to evaluate the performance of a model that we learned on the training data with respect to the data that was held out from training or the test data. And in this case, we may use something like the squared error rather than the classification error to measure the quality of our performance, as I've illustrated in this equation here. So we're just taking the squared error between our label and our model prediction, where we determine W using our training data set, and the set of indices Q1 represents our test data or our holdout data. So we can find the average squared error over that set, and then you can combine those squared errors over multiple holdout sets to come up with a global cross-validation score and use that to decide what the appropriate complexity of your model should be. So cross-validation is a general principle that can be applied to a whole range of problems, and different problems it may be appropriate to use different performance metrics, like classification error in a classification problem, perhaps squared error or another type of error in a modeling problem.